Okay, so I will let you introduce yourself.
Okay. Yeah, thank you very much. I'm Jeff Dionne. I'm from the J-Core project, also Core Semiconductor. Today we're going to talk a little bit about the J-Core processor, the platform that we built, the experiences that we had doing that, and what it means to build completely open silicon, completely open devices, not only chips, but also products based on open source. As some of you may have heard of the J-Core platform, it's basically the same ISA as Super H. That's still trademark, so we can't call it Super H, but the developers of J-Core are some of the same engineers that did Super H years ago at Hitachi. And you might say, well, why would you want to do a new thing? We've got RISC-V. Well, we came before. The J-Core project is now 12 years old, so RISC-V is a newcomer. We've been around for a long time. Basically, the simple J-Core platform is a 5-stage pipeline. This is what we deploy in real products. There's other implementations also, but it's kind of parallel. It has a few different components in parallel with the integer pipeline. So it's a pretty interesting thing. And as you'll see, the choice that we made to choose the Super H ISA instead of something else came about for real reasons, not a choice because we happen to like it or that's the case. Specifically, though, J-Core is not a CPU project. What it is a platform that lets you build things. Today, the most important takeaway from this is if you want to make something that's like an IoT device, a memory-connected device, something that does sampled data, something with a DSP, J-Core is for that sort of thing. If you just want to make something that connects to the internet or runs Linux, then probably RISC-V is better. But if you ask the question, where do I start if I want to build a product? If I want to build something and I want to build it completely open source, what do you start with? It depends on what the requirement for that is. In our case, just about everything we make is signal processing. And what I'd like to say is, at the end of the day, when you really think about it, even something like a cell phone is a mixed signal device. It has radios, it has sampled data. It's not the case that essentially everything is an application platform. If you want to do that, then there are other choices. But for things like this real-world device in the background here, this is an energy monitor. Basically what this does, I'll show you in the next slide, is it measures voltages and currents, time synchronized to GPS time, on the energy grid. And this is for renewables integration. This is why we developed the J-Core platform inside the company in the first place. Obviously, we're talking about many DSP cores. There's something we call the S-Core DSP. This particular platform has 24 DSP cores on it and a bunch of hardware accelerators. Up here, in each of these analog blocks, there's an ASIC that we did that has a very high resolution delta sigma converter with time synchronization for simultaneous sampling. This is the kind of thing that you can do with open source hardware today. And that's really important. That's why we did this. So what do I mean by energy sampling? So here, if you look at this diagram, going from generation through transmission to distribution and even residential customers, what is it that you need to do? Well, it turns out that in the universal case, you want to sample these signals at a very high rate, about 12 megasamples per second, and you need extremely high dynamic range, over 140 dB, really close to the thermal noise. And the reason you need to do this is because you want to see all the reflections on these transmission lines in order to calculate where faults are, where discontinuities are. That's neither here nor there for what we're talking about today for J-Core, but this is where the platform came from. So if you think about the requirements that are necessary to do this, obviously just a generic compute platform isn't going to do it. But what we found, as I mentioned, is this becomes rather generic. So the J-Core platform itself is much more than a CPU that you can run Linux on. You can do that, but it also has very high-speed DMA. So for instance, if you need to do something like this energy monitor, you might need 64 channels of time interleaved DMA that give you the capability to look at these signals while doing it all in real time. We have S-core DSPs, fixed point DSPs, so you can actually do something with the data that you got. We have a GPS receiver intellectual property that you can put there. You still need an RF outside, but everything else is inside. And you can stick your custom IP in here because your application will be different from ours. So as a platform, you inherit this kind of thing in good open source fashion, and then add to it what it is that you need to do to make your product. So let's talk about one little part, for instance. You know, the first GPS receivers, they look like this, right? Nowadays, this stuff here is an IP core. And in our platform, this is the software that runs on it, running in the background here. This type of digital block and analog block are really small, but they're kind of unheard of in the open source. And what we want to do with the J-Core project is make it so you can make sensor nodes, so that you can make IoT devices, so that you can make these kinds of connected things that do sample data easily with an off-the-shelf platform, with an off-the-GitHub platform. And that's basically what we're doing. So we did this for precision timing, but that also means that you want to do stability of the tracking loops. And if you're tracking satellites, you need to do it in real time. It leads to one of the things that I think might be a little bit interesting about this talk. There are some things that are not intuitive that we found as we went down this process. Yeah, and one of them is the control flow, closed loop controls. So, well, they say the instruction set architecture doesn't matter, but it actually does matter, except it matters when you're doing things that are non-conventional. So if you have, for instance, just a generic RISC architecture, what you find is that the memory bandwidth that the device needs in order to sustain the execution of the programs you're trying to run gets in the way of other things like sampled data, like DSP functions. And so the ISA that the J-Core offers is a compressed instruction set architecture that drives a standard RISC pipeline. It's really quite interesting when you look at what that does in terms of memory bandwidth and memory usage. As the program size decreases and as the density of the instruction set increases, the pressure on the memory system decreases. And that leads to things like real time is equivalent to larger buffers. Everybody says that. That turns out to not be true. How do you do a closed loop control system if your buffers are really long? Your control loop will be unstable. So in order to do that, you have to have these kinds of considerations where real time is everything. It's safer to use a common off-the-shelf system, except when it doesn't do what you want. Like, how are you going to do a tiny IoT device? You know, this is Taiwan. Everybody builds chips. Everybody builds devices. So this is not a big deal. But in North America, people use a Raspberry Pi for things and then struggle to do something really simple. Starting with an FPGA like this, or even doing an ASIC with it, that's pretty simple. But nobody does that, except everybody does. So embedded IoT is a niche use case. This is one we hear all the time. So the J-Core processor is built on Super H. There's millions and millions, hundreds of millions of devices with Super H architecture in. Many more than RISC-V. Many times more, many orders of magnitude more. This is a tested platform. And not only that, but there are many, many times more embedded devices than there are mobile phones and PCs. So this kind of thing is the mainstream platform. And if you build it, they will come, but it's not necessarily true. So we built this platform almost 10 years ago, and we still need to get the message out. So thanks for listening. This one is true. Hardware moves faster than software. And we heard that earlier today on, when they were talking about backwards compatibility with CUDA. It's really important to understand that your hardware needs to be supported by software flows. So some counterintuitive results, Linux often just gets in the way. The interrupt service routines in Linux are really long. It doesn't real-time schedule. It's a bottleneck for most embedded devices. And signal processing doesn't mix into it very well. So you need an RTOS on the front end. You need a real-time operating system as a layer. And that's one of the places where J-Core really shines. If you need a small processor to do something, you can stick it into the system and then not worry about your interrupt latency. They just put it as an adjunct and run Linux as an application processor. A thing is an integrated solution. It doesn't matter if I've got an application running on my PC. If I need to build a product, it all has to go together. And that's sort of a counterintuitive result because you think about software as a portable thing. So maybe we'll move on from that for a moment. What does a modern device look like? A modern device kind of looks like this in the generic sense. Sensor inputs, and then that can be analog to digital converters, it can be radios, it can be anything like that. Some kind of real-time processing that talks to the radio, and then output interfaces, which are also analog and real world. And so this kind of integrated flow is what's driving the process node that you choose for your hardware. It's what's driving the hardware that you build. And then below that is the non-real-time processing, the kinds of things that you get from Linux and the OS and the storage. The other part that's really important today is encryption and decryption. We find that just about every system we build needs to be secure. But what's really important is if you don't understand the entire system, if there are closed source parts in there, if there's parts of the system that you don't control, then it doesn't really matter if you've got encryption. You don't have security. So an open system is very important. And this diagram is quite old. We made this diagram for a previous project. Okay, so towards a generic platform, what would you do if you wanted to start a product today? Well, one thing that you typically want to do is run it on real hardware. And so we built an FPGA platform that some people who are here may have heard of. It's called the Turtle Board. Essentially what it is a very small platform that lets you put your RTL code, your CPU cores, connect to it, sensor interfaces to a hat, and run Linux on that, run a real-time OS on that, whatever it is you need to do in order to build your product. And then from there, you inherit from our project or from another project, from maybe a RISC-V project, top-level RTL, tool flows, headers, operating systems. So within a couple of minutes, you can have something running that you can start to do your development on. And I think that that's really very important. In the background of the next slide, let's show you this is an example of a development we did ourselves on that platform. This here is a VPN device. We started at the beginning of the pandemic. We thought, what can we do that might be interesting during this time? And we took the Turtle platform and developed a hardware VPN. So the cryptography is in hardware, the key management's in hardware, the crypto engines are in the center in sort of a DMZ type of environment. There's a full CPU core in there. And then on the other side of it, there's high-speed CDC ECM, basically Ethernet over USB to the PC. And this kind of a product development, starting from the Turtle platform, can be done in maybe 2 months, maybe 3. It took us about 3 months to do. So this is basically the architecture. So over here, Linux is running on two J32 CPUs. And then in the center, completely separated by mailboxes, is a trusted compute engine with a J1 and hardware, ECDSA and Cha-Cha-20 Poly 1305 hardware accelerator for cryptography. And then on the USB side, a J1 CPU talking to USB as an RTOS. So all in one small board. And I brought them with me so if you want to see. So this is what the end device looks like. On the bottom is the CPU card, and on the top is the analog interface. And it really just starts with the concept. You know, what is it I want to build? And you start drawing out what the RTL flows would look like in order to put something like that together. On that side, you've got the Linux system. In the middle, you've got the cryptography, and on this side, you've got the USB controllers. And then the FPGA in the middle connecting to various different things. It turns out that the hardware itself is pretty simple. So that's nice, but what about taping out? Well, here is the example that I was talking about a little bit earlier. This is a J1 Super H CPU. It's about 45,000 gates, 0.3 millimeter square in 130 nanometer Skywater process. This is okay. We get to about 85 megahertz. It's not stellar. This is using the open plane flow. It's small enough that you can put it on a chip and it doesn't cost you all that much money. But the problem with the open tools now is that they're not quite up to the task. The CPU itself will reach time enclosure. And we have pretty good confidence that that's the case and it will actually work. We taped this out twice. But when you start to use this macrocell with other blocks around it, the open tools still have a way to go. But nonetheless, you can still do it. And this is the same RTL that we then used. This is the larger part of the chip to build something like this. Really simple. How can I demonstrate the smallest possible system? Well, how about a calculator? This is an ICE40 FPGA. The ICE40's $6. You can just buy them off the shelf, stick it on the back. It has a J-Core CPU, 32 bits, all the memories on board, and this runs FreeBSD, which is the equivalent of an HP calculator, except extended. So it's not, four function plus and minus, and this is a really interesting calculator. It's an engineer's calculator, arbitrary precision. And what we prove with that is it's almost cost competitive today to do a custom chip in something like an ICE40 as it is to buy a 32-bit microcontroller off the shelf. There's almost no need now for small, 48-pin Micron that you buy from, MediaTek or ST Micro or something like that. So J-Core is a good fit for mixed signal chips. I mentioned that earlier. This is proof. Here's a J1 that still has enough space in the ICE40 FPGA to do, for instance, a delta sigma modulator. I can do a D to A converter on there and get 12 bits of resolution without breaking a sweat, even just with the FPGA. So this is really exciting. Things are finally getting there. And the good thing about this is complete with all open tools. Not a single closed source tool was used to develop this platform. From the board layout through the FPGA synthesis to the place and route to the timing closure to the compilers to the application code. Absolutely everything open source. Okay. So it's mostly there. But how do you get, for instance, all of those tools together on your desktop so you can do it? OpenLane is this gigantic thing. It's about a gigabyte to download. It takes forever to build. Well, it turns out that it's not. There's only about 2 megabytes worth of real code in OpenLane. We stripped it out. And we made a builder for OpenLane. It takes GHDL. It will integrate GHDL with Yosis, with ABC, with NextPNR. It'll give you all of the SPICE simulators that you need to do the analog side. It gives you all of the PDKs you need in order to target Sky 130. Everything comes out of that, and you can do both the calculator design and prove that it works in real hardware, and then you can tape out on Sky 130 just with that. And it's a little bit finicky right now. We're still in the process, but it works. If you get it installed, you can actually do it. So simulation, synthesis, physical layout, LVS, compilers for bare metal Linux on J-Core, and electrical and gate level simulation if you want to actually go that far. Unfortunately, if you want to do something like the larger device, the VPN, the open source tools are just not there. So you're going to need some tools from the vendor to do that. The Xilinx ISE or Xilinx Vivado or the equivalent from Intel. And on the software side, there's two ways to go. We often say that Linux is what comes after C, right? Like if you want to build a device that talks to the internet, you really are talking about Linux these days. So that's the second flow. For that, there's Muscle Crossmake. By the way, it also comes with the open lane flow that we had in the previous one. And for bare metal, you want to use what's called minimal lib. Essentially, what that will do is get you bare metal compiler with a bare metal C library, everything you need to write programs on a bare device in less than 200 bytes. Okay, so 200 bytes, not 200K, 200 bytes. So you can really do that in almost no space on your FPGA, or if you have a very small C RAM block on your ASIC. Okay, so is this really real? Like, can you really do real products with it? Well, you bet. So here's that energy monitor I was talking about. And here's a board that we did for a fairly large company that is part of that. This is a turtle board I was talking about. And that's an SoC module that goes into a device that is an energy monitor. And here's that VPN. I have some of these with me. We can look at them, or if you want to see. So I want to try a demo of the energy monitor. This is actually a picture of my bench before I left Japan. And if the network cooperates, maybe I need to grab my cell phone. We'll see if we can do it. And turn on sharing. Whoops. And then exit from there. Sorry about this. The vagueness of doing demos in real time. Good. Maybe yes? Yep. Okay. So here is an actual J-Core multi-core system running Linux with analog inputs, those Delta Sigma inputs from the power grid running on my bench right now. And if we go over here and take a look, shall it come up? Maybe we don't have enough bandwidth. Yep. This is what the power grid looks like in Tokyo right now. So this is the voltage waveform, and here's an incandescent light bulb, and this is an LED bulb running right now in Tokyo. And that's supposed to be the phase angle of the power grid with respect to GPS, but we didn't seem to get it at the moment. It's okay. So where's my cursor? Yeah. Yeah, so I want to thank the sponsors, obviously the COSCUP and Tsai for having us in, but also Smart Energy Instruments and Core Semi for doing the platform. J-Core.org if you want to build something really cool. This is definitely a live project. A lot of people wonder where we are. We're doing real world projects. Block and Space Chain and Arcturn, some of our funding partners. So how do I get started? Well, support open hardware and make something cool. Thanks.
Thank you so much. We have about 3 to 4 minutes, so maybe 1 or 2 questions.
Any questions?
Okay. Just come get the microphone. Yeah.
Hey, thank you for your very impressive project. I have so many questions. I think I'll just pick 2. And you said that you picked the Hitachi Super Edge because of its smaller instruction size, and it really released the bus bandwidth. Can you go into more details? Because I don't know how much that will impact the performance or the real-time property.
So there's really 2 parts to that. The first part is that the instruction width is fixed at 16 bits. And so suddenly you have half the memory bandwidth there. But that's not the end of it. Instead of that simply being a compressed instruction set like the RISC-V-C, right? Those instructions actually represent constructs that the compiler will emit. So there are multiple RISC instructions that are implied by each 16-bit instruction. And so the compression that you get is more than just the compression of 16 bits out of 32. So you get probably 3 to 4 times the memory efficiency on the instruction side of the CPU than you would get with a RISC-V or with anything that's similar to that. Yeah. Does that help?
One quick question. You said you tape out with the Skywater 130 nanometers with only up to 85 megahertz frequency. That is not high, I think. And I wonder how much frequency you can get on the J1 on ICE40.
Yeah, so J1 on ICE40, just synthesis without doing any optimization, you get about 14 megahertz. So it's really small, right? But it turns out that the critical path can be optimized. We just haven't done it. And so far as the Sky 130 is concerned, the problem is really the tools. You don't have the choice of doing, individual blocks. You would do the ALU, you would do the register file, you would do all that stuff separately. But the open lane flow or the DARPA open road flow doesn't really have the capability to put those blocks together except in one great big massive amorphous blob, right? Like, as you were seeing, it's just a big blob. This is not how it should look. It's not supposed to look like this, right? This is the best you can do with open road and open lane as it stands right now. Do you have one more? Or?
Yeah.
Well, okay.
Maybe I can add an information to this. We are struggling in the same problem with the frequency, and I can tell you that with the commercial tools you can get factor 2 at least out and even if this depends on the supported or on the library. If you have register or multi-bit register, then it might be even improve the design and the speed. Yeah. Okay.
Yeah, I think my point is that we all need to, as open source community members, we all need to look at the tools and say what pieces are missing, right? Like, we need to actually do these flows and say, oh, well, this didn't work very well, right? And own up to the fact that this is a hard problem. We need to look at the tools and say, right now I have to look for standard cells that are going to do something really useful for me here. I need register file blocks that I can rely upon. I need SRAM blocks. Like, this is ridiculous SRAM, right? Like, there almost no there's not enough SRAM for that size. This should be 16 kilobytes. It's like 128 bytes. That is not a reasonable thing. So there's still stuff to do on the open side, but it's an exciting time because suddenly it's possible, and it wasn't possible before.